Hey guys, here's your review for Spiral 3. We're going to start off again with the solving linear equations and inequalities. This is the third time that we've seen something, so it's going to be on our spirals for once more. First one up, we've got something with fractions again. You might get the hint that this is going to be really helpful for the rest of the year, which is why we keep focusing on this. And the big idea here is I might want to try to get rid of both denominators at the same time at the very beginning of the problem. And I also might want to take care of this distribution at the very beginning so I don't have to worry about anything else. In fact, I'm going to do that first so that my multiplying by denominators ends up a little bit easier. And in doing this, so it's going to be negative 2x and minus 24. Okay, I'm going to copy everything else down just so we know where we're at. 5 plus 2 equals 4x over 7. Okay, I'm going to multiply both sides of this equation by whatever my common denominator between 5 and 7 is, which happens to be 35. The nice thing here is that as we do this, some of these are going to cancel out. So if I do 35 times 3x minus 4 over 5, I can reduce this before I multiply. It's going to make my life easier, because 35 divided by 5 is going to be 7. That's one of the things that I saw missing in the last spiral. Okay, so we've done that one. 35 times 2 is going to be plus 70. 35 times 4x over 7. And again, we've got 35 divided by 7. That can reduce to multiply by 5. 35 times minus 2x is going to be negative 70x. And 35 times 24 is going to be a number I don't really want to deal with, but I think it's going to be something like negative 840. It's going to be 12 times 70, which is 840. Okay. So here we've gotten rid of some of this stuff. My 35 and the 5 are gone, so we get 7 times 3x is going to be 21x. 7 times minus 4 is going to be minus 28 plus 70 equals 5 times 4x is going to be 20x minus 70x minus 840. Let's combine some like terms. 20 minus 70 is going to be negative 50. And if I add 50x to both sides, we end up with 71x. Minus 28 plus 70 is going to be 42. And on this side, we still have a negative 840. So we get 71x minus 42 to both sides. And we end up getting negative 882. Finally, I have to finish this problem up by dividing. Divide both sides by 71. And we get x is equal to negative 882 over 71. I don't think that can be reduced. Although I certainly could be mistaken, so you can certainly stop at this point. You do not need, excuse me, kiddos, you do not need either a decimal approximation or to try to reduce that. Next problem, we've got an inequality. Oh no, this one has some absolute value stuff. That's going to mess some things up. Let's think about what absolute value means. And actually, we're going to start by graphing this one, just so we can understand what's going on here. And what I'm going to do is to choose some points and see if they work. Okay, I'm going to plug in 0 first, and I get 0 minus 5 is greater than 3 in absolute value. That's true because negative 5, absolute value makes it positive 5, so 0 actually works. Okay, I guess that's kind of interesting. Maybe I'll bounce around a little bit to see if there's anything that I can get not to work here. I don't know, how about like negative 5? I am just guessing things kind of at random, so we're not really worried yet about what's going on here. And negative 5 minus 5 is negative 10, which absolute value is still greater than 0. Okay. What about a really big number like negative 100? Okay, well, let's see. Negative 100 minus 5 is still going to be greater than 3 when you do the absolute value. It looks like there's a lot of numbers down on this end of the grid that are going to be okay. I wonder if there's a point at which that stops being okay, because 0 was okay. Negative 1, negative 2. Well, negative 1 minus 5 is negative 6. That works there too. Negative 2 minus 5 is negative 7, which the absolute value is positive 7. It looks to me like all of these numbers all the way down here do okay. Okay. What about some positive numbers? Okay, well, 1 minus 5 is negative 4. Negative 4, absolute value is 4, which is bigger than 3. Okay. 2 minus 5 is negative 3. And I'm going to write this one out. So 2 minus 5 is negative 3, and negative 3 is not bigger than 3. Oh, man. I think we found an endpoint. Because if I plug in anything up until this value, I get something that works. Okay, I'm not convinced that we're done. What if I plug in a really big number like, I don't know, 42? Well, 42 minus 5 is going to be 37, which is bigger than 3. Huh. And I guess if I put in even bigger numbers, that probably also works. This is getting weird. So now we got stuff on both sides there. What would happen if I went for an even bigger number? Then I'd probably just keep getting numbers that work. I wonder if there's a place that this stops on this side. Let's try a few. Does 6 work? Sorry, not even near 6. So we're at 2. Does 3 work? 3 minus 5 is going to be negative 2. Negative 2 is not greater than 3. Okay, how about 5? 5 minus 5 is 0. 0 is not greater than 3. I wonder where it starts up again. Oh, 6 minus 5 is 1. No. 7 minus 5 is 2. 8 minus 5 is 3. Okay, now we're getting somewhere. So 8 minus 5 is greater than 3. And it's not. So we have one stopping point at 2 because 2 minus 5 is negative 3. We're going to have another stopping point at 8 because 8 minus 5 is going to be positive 3. And all the numbers in between there don't work, but all the numbers on the outside do. That's a graphical way to think about this problem. An algebraic way would look something like this. So the absolute value of x minus 5 is greater than 3. I know that absolute value makes anything inside positive. So we're going to have two different cases that we think about. If we know that x minus 5 is positive, this pretty quickly solves to x is greater than 8. And that makes sense for this part of our grid up here. What if x minus 5 is negative? Well, the way that I represent that is by saying negative x minus 5 is greater than 3. I can distribute, and I get negative x plus 5 is greater than 3. I might subtract 3 and then divide by negative 1. I'm sorry, subtract 5. I get negative 2 on this side, negative x on this side. Remember, when I divide by negative 1, the other thing that I have to do is switch this inequality around so we get x is less than 2, which is the other piece we have up here. This would be an OR inequality. The answer to this in words would be that x is either greater than 8 or it's less than negative 2 for this to be true. More on absolute value equations in a few minutes. All right, now we got some slope stuff. If you're asked to write an equation for a line passing through 2 points, point slope is often our best bet. I like the version that's y1 plus m times the quantity x minus x1 because I like the starting point plus the change that this tells us about. And really what we have to do is find the slope and then plug some things in. So my slope might be k minus 15, and on the bottom it's going to be h plus 12. Okay. I can choose either of these points as my value for dealing with x1 and y1. I'm going to use the numbers, and that's okay. I'm going to do one with the variables too. So we get y is equal to 15 plus k minus 15 over h plus 12, x plus 12 on the bottom. You don't have to do anything else. You could stop here and that would be totally fine. This could also have been y is equal to, using the h and k value, k plus k minus 15 over h plus 12, and we get x minus h. Okay. A second way for us to do this is using y equals mx plus b. Often we don't like that, especially dealing with things like that, but we can work with that a little bit here. We already got our m, and I could use the point 15 and negative 12 to get something like 15, that's my y, equals slope k minus 15 over h plus 12, and then I need my x, well, it's x, and then plus b. Oh, we have a number for x, right? Negative 12. Negative 12, and plus b, which is the thing we don't know. If I multiply this through, we end up with 15, remember that's negative 12 over 1, is equal to negative 12k. And negative 12 times positive 15, I want to say it's like 180, okay. Plus 180 over h plus 12 times 1, so we can leave that the same, plus b. A perfectly acceptable answer for this would be 15 minus 12k, negative 12k plus 180, over h plus 12 is equal to b. Plugging that in into y equals mx plus b, you get a really ugly equation. K minus 15 over h plus 12, x plus 15 minus negative 12k plus 180 over h plus 12. There's a reason we tend to like point slope better dealing with things like this, because that's gross. It works, but it's gross. Next one, I'm talking about line M is perpendicular. I want to think opposite reciprocal slope to the line 5x minus 3y equals 4. 5x minus 3y equals 4. Might be helpful for me to put this in slope-intercept. So negative 3y is equal to negative 5x plus 4. Divide both sides by negative 3. We get y is equal to positive 5/3 minus 4/3. Sorry, I forgot an x in there. Okay, this is the slope of the natural line. We want the reciprocal opposite, so negative 3/5 is Rm. And we go through the point 2, 13. One way of writing this would be y is equal to 13, that's my y1, plus negative 3/5, that's my m, x minus 2. And another way of writing this would be y is equal to negative 3/5, x plus b, and plugging in this point in order to figure out what b is. So 13 is equal to negative 3/5 times 2 plus b. 2 times negative 3/5 is going to be negative 6/5, and I've got to add that to the other side. So 13 plus 6/5 I'm going to convert this to decimals because fifths come as a nice decimal. That'd be negative 1.2. So 13 plus 1.2 is going to be 14.2 is equal to b. Our equation would be y is equal to negative 0.6x. It's nice to keep everything in decimals. Plus 14.2. If you want to leave that in terms of fractions, you can have something over 5. It's going to be 65 plus 6, 71 over 5. I don't know that you want to do that, but you're welcome to if you'd like. X-intercept and y-intercept. To find the x-intercept, we got to plug in 0 for y. And to find the y-intercept, we got to plug in 0 for x. To be honest, I kind of like this equation better at this point because I don't have to do any math, and that's kind of nice. So let's take that equation, plug in 0 for each of these things. So 0 equals negative 0.6x plus 14.2. I'm kind of regretting not leaving this in fractions now, which means that 0.6x, so 0.6x, is equal to 14.2. Divide both sides by 0.6, and you're going to get some kind of a value. And we get 14.2 divided by 0.6, 23 2/3, which is 23.6, repeating, keeping it in decimal form. That's my x-intercept. The y-intercept is much easier because the y-intercept is b. Next up, we've got to graph a piecewise function, and here we've got 3 lines that make up a total piecewise function. We got to see what's going on here. I apologize for the growling in the background. Those are the dogs. First up, we've got 2x minus 1 is if x is less than or equal to 0. Negative 2x minus 1 if 0 is less than x, which is less than or equal to 3. And then y equals negative 7 if x is greater than 3. A couple things I'd like us to notice. This notation is new to us, and it's written like this in lieu of what we've been doing with braces. This means the same thing as 3 separate lines where each of them could be written like this: y equals 2x minus 1 with the domain x is less than or equal to 0. The standard notation is this. What we've been using is kind of a modified notation that I find useful to help us introduce the concept, but we can move from there to this to make it a little bit easier for ourselves when we see other texts. So if x is less than 0, I'm going to make a barrier at 0 just to kind of keep track of that. I'm going to do the same thing at the next boundary, which is 3. Okay, and then I'm going to try to draw these things. So 2x minus 1, that means I'm going to have a y-intercept of negative 1 and a slope of 2. I'm going to go backwards because I know in advance that this is the negative side. So that's really only going to apply down here. And with a less than only, we're going to have an open circle at the end. Next thing, negative 2x minus 1 between 0 and 3. Thankfully, we're already starting at 0, so we can use the y-intercept again. This time it's going to be... I guess that first one should have been a closed circle anyway, but they overlap, so it doesn't really matter. So negative 2x from here means that we're going down 2 over 1, down 2 over 1, down 2 over 1. And then at 3, that's my next endpoint. I have a closed circle. Okay. Finally, we got negative 7 if x is greater than 3, so negative 7. Oh, so this is going to be a horizontal line at 7, but starting at x equals 3. And what we ended up forming here is kind of a zigzag line that all three of these things are connected. I guess that's about it for this one. For the next part, we're going to look at what this new notation means. This we're going to read as f of 2, and I'm sorry, f of negative 2. And what f of negative 2 means is plug in negative 2 for x. Which x, you say? Well, we're going to look up here and decide which of these three domains negative 2 fits in. Since it only fits in the first one, we're going to plug it in to the first equation. So I'm going to plug it in here. So we got 2 times negative 2 minus 1 is negative 4 minus 1 is negative 5. And we're done. F of 0, that's going to be the same thing. We're going to plug 0 in for x. And it looks like that's going to tie to the first one too, because this one includes 0 while this one does not. So I'm going to plug it into the same equation. So 2 times 0 minus 1 is equal to negative 1. And finally we're going to have plugging in f of 13. F of 13. And the first thing I have to do is decide where to put this in. The only one of these three that 13 goes with is this guy, because 13 is greater than 3. And there's nothing to plug it in there because this is a constant. So this is the value of 13 is my final answer. There's kind of a bonus question here that asks something about continuity, whether a graph has any jumps, holes, or gaps. A really handy way to think about continuity is, could I draw this without lifting my pencil? So if I were to start down here, I can go up, down, and keep going. And even though I have some angles in here, I don't have to lift my pencil, or in my case my stylus, in order to draw this graph. Because of this, this would be called a continuous graph. And we could call it continuous because we don't have to lift, or because none of these things, no jumps, holes, or gaps exist. Zooming out a little bit. Finishing up, we got some absolute value graphs and equations. Go look at the absolute value graph first. And we talked about a way for us to look at this. All absolute value graphs are based on a graph that's centered at 0, 0, and has a slope of 1 on either side. What would be helpful to us is to understand how that changes to get to this one. The first thing we've got to know is that inside the parentheses, as we talked about this week, minus 7 means we're going to move 7 to the right. Outside, adding means we're going to add 5 as we go up 5. So 7 to the right and up 5. 1, 2, 3, 4, 5, 6, 7. Up 1, 2, 3, 4, 5. Here is my vertex at 7, 5. Okay, second part of this is to use this slope type number out in front. And what this really means, we're going to go down 1/3 as we go over 1. Since this is a linear-like function, we can treat this just like a line and go down 1, right 3, and mirror that on the left side, down 1, left 3. So we're going to keep following this pattern. All the way down. And all the way down this way. In order to find intercepts, we're going to have to plug in 0 for x and for y. The y-intercept, if I plug in 0, I get negative 1/3. 0 minus 7 is negative 7, but we have absolute value, so that's positive 7, and plus 5. So we've got negative 7/3 plus 5, which 5 is the same as 15 divided by 3, or 15/3. So 8/3 would be my y-intercept. To find the x-intercept, I've got to plug in 0 for y. And we get 0 is equal to negative 1/3, the quantity absolute value x minus 7 plus 5. I'm going to get the absolute value part by itself first. We're going to see this again down below. And I'm going to do minus 5 and multiply it by 3 in order to do so. Multiply by negative 3. So minus 5 times negative 3 would be positive 15 is equal to the absolute value of x minus 7. As we're going to talk about again in a few minutes, the absolute value gives us two conditions. I'm going to do these over here. That 15 is equal to x minus 7. That's the standard condition where this is positive. And what that gives us is that we have an x-intercept that 22 is equal to x. So if I could keep going way over here, I'd probably hit, and that looks about right there. The other condition would be if x minus 7 was negative. So 15 is equal to negative x minus 7, or 15 is equal to negative x plus 7. If I subtract 7 from both sides, I get x is equal to negative 8, which I think pretty close with my sketching graph. So I'm pretty proud of that. Okay, moving onward, we got some absolute value equations. One of the reasons that we hit some of the algebraic equations of high difficulty hard this year is to make these feel a little bit more comfortable because we got a lot of stuff going on here. First things first, in each case we're going to get the absolute value piece by itself before we do anything else. So for the first one, that's going to be minus 1 to both sides. And we'll get the absolute value of 2x plus 1 over 5 is equal to 6. Multiply both sides by 5. We get the absolute value of 2x plus 1 is equal to 30. And from here, we're going to work on understanding the absolute value. Absolute value gives us two conditions. One, that's true if the inside is positive. And that would look like 2x plus 1 is equal to 30. That's if the inside gives us a positive value. We subtract 1 and divide by 2 to get x is equal to 29 over 2. The second condition is going to occur if the inside were negative. So negative 2x plus 1 is equal to 30. In other words, negative 2x minus 1 is equal to 30. So I got negative 2x, I'm going to add 1 to both sides, equal to 31. And when I divide by negative 2, we get x is equal to negative 31 over 2. What we really need to do in order to verify these work is plug them back in. For this particular spiral, I'm going to give you one that has two answers that work. As we move on, we're going to see the possibility of answers that come out algebraically but don't actually work. And we're going to look at why that happens too. Finally, we're going to do the other one. So I might add 12 to both sides. And then I'm going to divide both sides by 3, leaving me with the absolute value of 4x minus 5 is equal to 12 divided by 3 is 4. Same thing, I've got the positive case where 4x minus 5 is positive, and that equals 4. I'm going to add 5 to both sides, divide by 4 to get x is equal to 9/4. And by the way, the reason I use these fraction answers is because it makes it much harder to guess. And guess and check is a strategy that students tend to try to use instead of actually learning how to do the algebra. And I really would prefer, in fact I require, my students to show the algebra because we need to understand how these equations give us some weird things. Same thing for this one, so we got 4x minus 5. And this is the negative version. This is what would happen if inside the absolute value was negative. And that's going to equal, what did you say, 4? Okay. So that's negative 4x plus 5 equals 4, which means that negative 4x, and that's plus 5 equals 4, so it would be equals minus 1, and x equals positive ¼ And again, I chose two that specifically have numbers that work for us. In future spirals, we're going to have to check these before we can declare that we're done.